And here we go. All right. So again, I want to talk about a few points from chapter 5, and then we'll pause, do our lecture break, and we'll do our quiz for today. So which specific proteins function to transport materials? And so this isn't dealing with simple diffusion, right? Simple diffusion does not require proteins to happen, according to the tables that we ended our time on yesterday. So facilitated diffusion, however, does. So this is still diffusion. It's still materials moving down their concentration gradient, but they either cannot move through lipid bilayers at all, or they can't move quickly enough to actually try to establish any kind of equilibrium. And so they need to be facilitated by proteins. And so we have channel proteins that have hydrophilic cores. And so those hydrophilic cores, they are polar. The amino acid residues there are polar. And so polar materials interact well in those cores. And it basically just creates a continuous environment. We talked about that last time. And so water uses what are called aquaporins, which is a type of channel protein with a hydrophilic core. But remember last time we said water moves by both simple diffusion and by facilitated diffusion. You'll see this in a few weeks, but cells produce an enormous amount of water. At least our cells produce an enormous amount of water. Keep that in mind. They have to do something with that. Then we have what are called gated channels. These operate with ions, allowing ions to move down their concentration gradients. And they basically come in three forms. You have open, and that's where ions are actively moving down their concentration gradient. You have closed, where ions are not actively moving down their concentration gradient. And then you have inactive, which is completely different than closed. Inactive means it cannot be opened. Closed can be opened. Another way of thinking about this is open, closed, and locked, right? And that's something we recognize, right? A door can be open, a door can be closed, or that door can be locked, right? Locked and closed, not very different ideas, but different ideas altogether. So yeah, ions tend to use gated channels and not channel proteins. All right, another type of protein that works with facilitated diffusion are carriers. And so carriers actually physically attach to a specific solute and then change shape to allow it across the membrane. Again, we're still talking about diffusion. We're still talking about some material moving down its concentration gradient. But that material is so important that the proteins that allow its transport physically grab it and change shape to move it into the cell as quickly as they can. Yeah, Joe.
So that process of changing shape, that doesn't use like any ATP or that kind of energy?
No, it's fueled by the concentration gradient itself.
Okay.
So it does use energy, but it uses the energy of the molecule wanting to move down its concentration gradient to do that. And so a way of thinking about this, you ever seen a football team run out onto a field and run through, like that poster that the cheerleaders are holding? Right? And so that thing's got to break, right? And it requires some energy to do that, but it's those football players moving down their concentration gradient that fuels that. That was a pretty good analogy. You're welcome for that. That one just came to me. And so these carriers, they're nice. They do a really good job of getting material in quickly, but because they actually have to specifically bind whatever that material is that's diffusing, they can become saturated. And so these are proteins that cells will oftentimes synthesize to add to the membrane when you have a point of saturation. And then when that point of saturation is gone and there's not that crazy concentration gradient anymore, the cell will oftentimes pull those proteins out of the membrane and recycle them. And so here's a channel protein, again, a protein with a hydrophilic core. And so it's just showing you the positive charges here, but if it's a hydrophilic core, it's polar. It's got positive and negative charges, allowing the materials to move through. Here is a gated ion channel. And here is this channel is open. Here it is closed. The way you can tell it's closed and not inactive is because it's still the proper shape. When they become inactive, their shape actually changes, and that's why they can't be opened. Their shape has to be changed again in order to allow them to be opened. So carrier proteins, again, these are proteins that physically attach to whatever that material is that's diffusing, moving down its concentration gradient. And so here you can see this material comes in, attaches there, and it triggers this change in shape, allowing it to move into the cytosol. And so what's driving and fueling that change in shape is the concentration gradient, probably the velocity by which that material enters into there, that kinetic energy can actually be harnessed to change the shape of the protein. In the same way, like the kinetic energy of a football team can be harnessed to rip through that poster, or the kinetic energy of a monster truck can be harnessed to crush a car, right? Do people still like monster trucks? I love monster trucks. My kids love monster trucks, so I guess I don't. It might just be my kids, though. They're kind of freaks, but they're it's just awesome. All right, so why is osmosis so special? Why do we have a name specifically for the diffusion of water? Why don't we just call it the diffusion of water? So yeah, I mean, the first point here is water diffuses like anything else. Water moves from an area of high concentration to an area of low concentration. But water in living organisms is never just water, right? It's a solvent. It's always got solutes in it. And yet it's still just individual molecules making up that solvent. And so you've got this weird dynamic in that on both sides of a membrane, it's water acting as the solvent, but there's more water molecules on one side than there is on the other. Yeah, so one reason why we give this a special name is because of the importance water plays to life itself. Water is just involved in literally every reaction that takes place inside of a living organism. And another reason, which I didn't actually write on the slide, is because water, the diffusion of water, we talk about that more often than we do the diffusion of other materials. Saying the diffusion of water over and over and over again would get really annoying, right? But saying osmosis, that just sounds awesome, right? Everybody wants a part of that. As long as you don't misuse it. Like if you say you're going to lay your head on your textbook and hope to learn by osmosis, it doesn't make any sense. Water is not moving from your textbook into your head. I mean, knowledge isn't either, but at least just talk about diffusion and not osmosis. All right. So another reason why we give it a special name is when water moves, crazy things happen, right? Y'all have seen that either firsthand or have seen some of the effects of water moving. And so water moving it's a very, very powerful force, even at the cellular level. When water moves, things happen. And so another reason is even though water is moving like other materials are by diffusion, the cells are always constantly controlling the movement of water. And so even though they are not investing energy to actually move each molecule of water across the membrane, they are investing huge amounts of energy to control which direction water is going to move. And so they are indirectly using enormous amounts of energy to control which direction water is going to move. And so again, part of the reason for this is cells move or cells generate an enormous amount of water. Every cell in your body is generating enormous amounts of water. And we'll talk about why that is in a couple of weeks. Another reason, so if water is a very powerful force, it would seem that you've got the potential to harness that powerful force and to use that energy to do something. And cells do that. Cells harness the energy of moving water to do a number of different things. And so yes, they invest a lot of energy into controlling which direction water is going to move, but they take advantage of how water moves. And then the last point of why osmosis is so special, why we give it a specific name, is that water will continue to move. Well, water moves all the time. I mean, water is constantly moving in both directions across the membrane. But when we're talking about net water movement happens until the pressure created by water actually moving, which is called the hydrostatic pressure. Okay, the pressure created by water actually moving equals the pressure associated with water's tendency to move, which is the osmotic pressure. So water will continue to move until the hydrostatic pressure, the pressure actually created as water is moving across a membrane, smacking into things, equals the tendency of water to move, which is the osmotic pressure. So osmotic pressure, if you want to think about it, it's like a potential pressure. In the same way you've got potential energy and you've got kinetic energy, right? You got potential energy, you got a boulder sitting on the top of the mountain, it's got a lot of potential energy, but it's not moving. Once it starts rolling down the hill, now it's got kinetic energy. So osmotic pressure is potential pressure. Hydrostatic pressure is actual pressure, but it gets to a point where they are equal, where water's tendency to move is coupled by the pressure created as water is actually moving. Does that make sense? Yeah.
So is that like the water's moving as much as it wants to?
Yes. Net movement. Yeah.
Okay.
Yep. Water is moving as much as it wants to. I like that. I mean, as if water actually desires things. Yeah, Mackenzie.
When do they equal each other?
At the point at which net water movement is zero. Yeah. And so, I mean, we see this in illustrating different solutions, and we'll actually go through this fairly quickly. So here's osmosis. Here we've got some kind of a chamber created. Here we've got a selectively permeable membrane, which will allow the water to move across, but won't allow the solutes to move across. And here, this water is distilled water. It's got nothing in it. Nothing in it. Anyways, we can talk about distilled water. No, wow, sorry. Happy Friday. Inside of here, we have a lot of solute. And so, in terms of if there's a lot of stuff dissolved in that water, that's places where water molecules could be, right? But instead, there's something else there dissolved in that water. So there's more water out here than there is in there, because there's places where there isn't water in there because something else is taking its place, right? And so water is going to move from where there's more water out here to where there's less water in here, and it's going to move all the way up until the point where the tendency of water to want to move there is coupled by the actual movement of water into there, to where those actually equal each other.
So basically until it gets what it wants?
Yeah, because as water, I mean, you can look at it this way, but as water's moving into here, it's ramming against the walls of this container, right? So as water moves into here, it's ramming against the walls of the container, and so that's exerting pressure out against the walls of the container, including this membrane. But water wants to move across that membrane because there's less water in here than there is out here. And so when the pressure exerted on this membrane is equal to water's desire to move across, then the net flow of water stops. Yeah, net flow of water stops. Yeah. All right. So how can we predict where osmosis will occur? Well, we basically have to answer this question: when is water less concentrated? And I just talked about this on the previous slide. Water is less concentrated wherever there are more solutes, because those solutes are taking the place of water molecules, right? A water molecule could be there, but instead there's something else there, like glucose. And it's not that glucose isn't important, it's just that the water would rather be in that position. And so, water interacts with these solutes, and so what we get is basically referring to less free water. And that's good language to use when we're talking about the diffusion of water or osmosis, is to use the language of free water. Where is there less free water? Where is there less free water? And so tonicity is a way of predicting this. Tonicity is just a measurement of the of a particular solute, So tonicity, again, it's the measurement of a particular solute. How concentrated is a particular solute? Sometimes you'll see osmolarity used instead. Osmolarity is the concentration of all solutes. Okay. So hypertonic solutions have less water, hypertonic solutions have more water than whatever you're comparing it with, which is usually the cell. Hyper meaning, I said more water, didn't I? They have more solutes. I started saying less, and that was actually true. They have more solutes than what you're comparing it with, which is usually the inside of the cell, therefore less free water. Hypotonic have less solutes, therefore more free water than what you're comparing with the cell. And then isotonic have the same amount of solutes on either side of the membrane. And so water is going to move to wherever there's less free water. And so if a cell is in a hypertonic solution, there is less free water outside of the cell in that solution than there is inside the cell, because there's more solutes. More solutes, less free water. Less solutes, more free water. Right? So if they're in a hypertonic solution, there are more solutes in the solution than in the cell. And if there are more solutes, there's less free water. And so water is going to leave the cell. And on your last quiz question, it asked you, in what kind of solutions will cells shrink? And almost all of you put hypertonic solutions. Almost all of you put hypertonic solutions. And so, yeah, this is what the cells invest energy to do. They invest energy not necessarily to move each individual water molecule, but to control the concentrations so that they can shape which direction water is going to move. You only need one. Okay. That's two. You need two. Do you want to? Oh gosh. I'm sorry about your backpack, Charles. How do cells do that? By actively pumping ions. We'll talk about that, but using proteins to pump materials against their All right, any questions? Yeah, Melissa.
You said about there's two words that are similar, like
So tonicity and osmolarity.
Okay.
Tonicity we use when we're referring to a specific solute. So, glucose or sucrose or whatever. Osmolarity is just the collective of all the solutes. All right. Please, 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 make sure everybody from the group has their name on this quiz. Don't leave anybody off. Hey, if they're not here, don't put their name on it. If they're in your group, but they are not here, they do not get credit for this group quiz Friday. Scratch those names off. I'll go around. I know mostly who's missing. I'll figure out everybody who's missing. All right, so here's the reading quiz. What provides the energy to fuel active transport? What are two types of active transport? And what are two types of endocytosis? Yes, sir.
Super general, just like a single man for them.
Yeah, that's fine. Yep.
What provides the energy to fuel active transport? ATP. What's GDP? Is Grace our scribe? Be our scribe.
Do y'all really only have two people from your group?
You just have 5.
Well, we're missing 7 people, so.
Active transport. That was facilitated diffusion. Yeah, but they use that for facilitated diffusion. There were three active transporters you're going to. I don't know. I don't think we need to get that complicated.
For which ones?
Sure.
Specific types of that first one.
No. No.
Okay, yeah, I don't think it's the channel protein. That one's driven by. So I think we could say like phagocytosis, right? That's active transport.
And then there's protein.
Yeah, because you're bringing it into the cell. Oh yeah, this is like endocytosis. We could say phagocytosis and endocytosis.
You're a little bit later than we wanted. I'm sorry.
It's all good.
You'll be good.
Yeah,
What?
thank you.
What's the other one? No, so you have passive transport. Yeah. And then there's passive, and then there's like facilitated passive transport. But then active is just active distribution. Active is distribution against the concentration rate. I don't think so. I'm pretty sure there's just one.
Okay, well, I think we might have like 3 things down.
Okay, cool. 2 types of endocytosis. Is there a question for? Are things for 2 and 3 kind of the same? 2 types of endocytosis and phagocytosis.
I just for the second one, I just
Oh, sorry, should you write down for the 3rd one? Phagocytosis and endocytosis.
okay, pass it around.
One more minute.
No, I didn't know.
1 more minute.
I'm cool with it. That's smart. You know a lot of this.
Talking about vacuum. Oh, so they're like different charges for the
You guys have this one.
All right, so wrap up any final thoughts you have.
And there's like instructions.
Thank you. No, I'll take them. I only do that because I don't want to have 30 sheets of paper I have to keep track of. I can handle 6. All right.
You want to know is ATP.
All right. So how does the cell fuel active transport ATP? For number 2, you could do primary and secondary, symport, antiport, several different ways in which you could describe that. Different types of endocytosis, receptor-mediated, phagocytosis, pinocytosis, what's that?
Phagocytosis?
Pino. I've heard it both ways. I don't know.
Is GDP, does that count as an answer?
GTP.
Oh,
Yeah, it's certainly not GDP. All right. So, our last 4 important questions to deal with from chapter 5. And as I told you, we will finish chapter 5 today, and we will start next week fresh. I think I don't even know what chapter comes next. You would think it's 6, but it may not be. It's on the reading list. 10? I don't know. It's on the reading list on Canvas. So plus I'll put the slides on today, and they'll have the chapter title on the slides. All right, so what if something needs to be moved against the gradient? Here we'll talk about active transport. How does primary active transport differ from secondary? How does the cell eject large molecules that can't be ejected through a pump? Exocytosis. And then what is endocytosis and the different varieties of it? All right, so what if something needs to be moved against its concentration gradient? All right, if something's moving with its concentration gradient, we call it diffusion. And it may be simple or it may be facilitated, or in the case of water, it's simple and facilitated. But active transport's always moving something against its concentration gradient. Therefore, you can't fuel it with the concentration gradient. And so if you can't fuel it with that concentration gradient, you've got to fuel it with something else. And in this case, you fuel it with ATP. Okay? But this allows the cells to do a lot of things. 1, take in essential nutrients, even if the cell has a lot. Some things need to be highly concentrated. You find this especially true in muscle cells that have to concentrate an enormous amount of calcium to facilitate the contractions. And so even though there's already a lot of calcium in it, they still need more. And you got to pump things against their concentration gradient. Also allows cells to secrete waste products or toxins if it's a cell that makes toxins, or just some product if it's like a cell in a gland, a glandular cell. And sometimes there's a lot of that product in the interstitial space, in that fluid around the cell. But they got to keep pumping it out because it's going to damage the cell. They also use this to maintain concentrations of hydrogen, sodium, potassium, calcium, really important ions. And all of these ions help to control the rate of water movement. And so this is why I said cells don't have to invest in moving individual water molecules, but they do invest energy in trying to control which direction water is going to move. And they do this by pumping ions against their concentration gradient and raising the overall solute concentration, either outside of the cell or inside of the cell. Also allows cells to set up electric potential or an electrical concentration gradient, an electrical gradient, also referred to as membrane potential. Most cells in your body are slightly negatively charged. The cytosols are slightly negatively charged. And so what that does is it creates an electrical gradient where positive charges want to move in there because there are negative charges to interact with, right? And so now you may have, in addition to a concentration gradient, having an electrical gradient. And it might fuel the movement of ions crazy fast. Crazy fast. Action potential. Anyways. There we go. Very next point. So neurons and muscle cells use this to generate what's called the action potential, where you rapidly change the charge on either side of the cell membrane, and as charges start to move, that generates electricity. That's what electricity is charge moving. And so now this generates an electrical signal that can propagate down the length of a cell and then bounce over to the next cell and keep an electrical signal moving down your body. I was having this conversation with my daughter last Saturday. And yeah, gosh. Anyway, she has an uncle who got in trouble for driving under the influence of alcohol. And he is very open about it, which is good for him, helping in the healing process. But it's a little interesting when a 6-year-old now knows that you shouldn't drive a car under the influence of alcohol and then wants to ask questions about that. But anyway, she wanted to know, why is that dangerous? And so we had a conversation about these electrical signals that move and how alcohol, interferes with those signals. And then she's like, well, what about coffee? Because I noticed, coffee helps mom wake up. So smart, my 6-year-old. And then so I got to tell her, alcohol inhibits those signals, and caffeine actually enhances those signals. And then she's like, so does it make you move even faster? So now she's all excited, I think, about drinking coffee, but she can wait. All right, so here's the action potential. We've got this setup where the cytosol of the cell is negatively charged. And here's this idea here. We've got this resting potential, a lot of negative charge inside of the cell. Something happens to open up ion gates and allow sodium ions to come flying into the cell, so much so that it takes the cell from being negatively charged to being positively charged. And when you have all that moving charge, it's an electrical pulse that actually propagates down the length of the cell. So this may be happening at one part in the cell, and then it triggers it to happen right next to that, and right next to that, so on, and just moves down the whole length of the cell really quickly, and allows you to move signals around a body much more quickly than pumping something into the bloodstream and waiting for the blood to carry it somewhere, right? Which should be a really crummy way to move your muscles, right? Your brain's like, man, need to move those fingers. Let's get something into the bloodstream and wait until it gets there. It's not good. It's not good at all. All right, so let's talk about primary and secondary active transport. So in primary active transport, the protein pumping the material also hydrolyzes ATP. ATP is used regardless. Whether it's primary or secondary, they're both using ATP. It's a question of, is the pump hydrolyzing ATP? Is the pump removing a phosphate group from ATP, or is a secondary protein removing the ATP, and then the process is fueled then by the concentration gradient of something else? So this is used for ions. Most ions, when they are pumped against their concentration gradient, are pumped using primary active transport, where the ion pump is actually hydrolyzing ATP as well. And so when you look at that protein, you see two very clear domains. One that looks like a pump, and then one that looks catalytic and actually looks like it could bind ATP. It looks like it's a perfect shape to bind ATP. And that's because it is, because it binds ATP, creates some strain in that bond, breaks that bond, releasing the energy, fueling the pumping of the ions. All right, yeah, so again, this generates membrane potential. It's also used to regulate pH in the case of hydrogen ions. And so our stomach does this. Okay, if you want to have an acidic environment, you need a lot of hydrogen ions, right? And so you have cells that line the stomach that actively pump hydrogen ions into that fluid of the stomach, lowering the pH, making it more acidic. Who knew? Who knew? You have what's called the calcium pump. This actually operates inside of the cell and is not on the plasma membrane. This is actually on the endoplasmic reticulum, controlling the sequestering of calcium ions inside of what's called the sarcoplasmic reticulum, which is a part of the endoplasmic reticulum packed full of calcium. Okay, but this is regulated moving of ions even within a single cell into a chamber surrounded by the endoplasmic reticulum or out into the cytosol. And that helps to control muscle contractions and other things like assembling cytoskeletal elements. The sodium-potassium pump, this is probably the pump that we know the most about, and it involves primary active transport, meaning it hydrolyzes the ATP. It also pumps both sodium and potassium. Pumps both sodium and potassium. And it pumps 3 sodium out for every 2 potassium it pumps in. Okay, so in addition to pumping both against their concentration gradients, right? It's pumping sodium out, giving you the idea that there's a lot of sodium outside of the cell, which there is, right? It's pumping it. If there weren't a lot of sodium outside of the cell, it'd just use an ion channel, right? Just open something up and allow sodium to move. But it's pumping 3 sodium out for every 2 potassium it pumps in. So in addition to setting up concentration gradients of both sodium and potassium, it's also setting up a charge gradient because it's pumping 3 positive charges out for every 2 positive charges it's bringing in. Right? You're losing 3 positive to get 2. That's a net loss of 1 positive charge, generating the negative charge inside of the cytosol.
Why doesn't it just pump out the positive charges?
Because it wants more than just a electrical gradient. It wants an electrical and a concentration gradient. Yeah, and you can't just pump out positive charge because that positive charge is in the nucleus of an atom. That's where the positive charge is.
Well, you know, they can't just pump out all the positively charged ions?
Well, it can, but it needs a lot of potassium inside of the cell because potassium repolarizes it. So after the action potential, when it goes from being negatively charged to positively charged because a bunch of sodium rushed in, it opens up a potassium gate, allowing potassium to diffuse out to help to regulate that. The repolarization. It's another story for another time. So in secondary, ATP is hydrolyzed by a different protein, setting up a concentration gradient that then fuels the active transport. And so you see this a lot where something will be coupled with one of these ion pumps. So these ion pumps will pump something against its concentration gradient to set up a concentration gradient. An ion channel will open up, allow those ions to move with their concentration gradient to diffuse and fuel something else, right? Because that provides energy as well. Concentration gradients? Yes? Yes. ATP provides energy. Concentration gradients provide energy. And then you have symport and antiport, which are 2 different types of secondary active transport. In symport, the solutes move the same direction as whatever the material being moved against its concentration gradient is. Sim meaning same. Antiport, the materials moving down their concentration gradient after you pump them against it are moving in the opposite direction of whatever it is you're actively transporting. So again, they both primary and secondary require ATP. It's just whether it's directly or indirectly. Primary, it's directly requiring ATP. Secondary, it's requiring ATP to set up a concentration gradient that's going to actually fuel the active transport. You're like, why wouldn't it just always be primary? Why wouldn't it just always be primary? It's an excellent question because some materials are too big to be pumped. Some materials are too big to be pumped, and they need to instead move through like a channel with just a hydrophilic core that are really big and provide the means for a lot of things to move through. And they're too big to actually be pumped. You know, they just need to move through like a tunnel. And therefore, you can't do it using primary active transport because they're too big. They're too big to pump. Instead, you have to fuel it by basically forcing it through as something's moving down its concentration gradient. Uniports. And so uniports a little bit different. They kind of fall into multiple categories. And so here's primary. Oh gosh, I thought I had to like trigger in each step. Here's primary active transport. Again, same protein is both pumping ions against their concentration gradient. You see a lot out here, few in here, going against the concentration gradient. Also hydrolyzing ATP. Whereas in secondary, it's indirect. Here's the sodium-potassium pump, again, the one we probably know the most about, sending 3 sodium out for every 2 potassium it brings in. Okay, so generating concentration gradients for both sodium and potassium, and then also developing an electrical gradient where there's more positive charge outside of the cell than there is inside. Symport and antiport. Here's symport. We developed a huge concentration gradient pumping these red ions outside of the cell with some pump. This ion gate opens up, allowing these to move down their concentration gradient, and then as they do, they pull something else along with them up their concentration gradient. And then antiport the driving ions. We set up this concentration gradient with a separate pump. This channel opens up, ions move down, and as they do, they facilitate something shuttling out against their concentration gradient. Make sense? Do you love it? You're like, it's Friday, and we're 12 minutes away from class ending. I don't know what to think other than I want class to be over so I can frolic off into whatever I'm going to do this afternoon. I get that. Hold on for a few more minutes. All right. So how does the cell eject large molecules? We're talking huge molecules. Huge molecules. So it does it through what's called exocytosis. And so when we talked about the endomembrane system, we said that the plasma membrane is part of the endomembrane system. And that's because a vesicle can leave the Golgi apparatus and then go and fuse with the plasma membrane. And when it does, whatever's inside that vesicle gets released to outside. And so that process is called exocytosis. Yeah.
Is that an example of secondary transport, or is that not the same at all?
It's not active transport, primary or secondary. Yeah.
So this is still a thing.
Yeah, it's a separate thing altogether. Yeah, it's a separate thing altogether. Now it could be either. You could look at it as, because it's kind of moving things, and we're not caring about concentration gradients. And so you usually see this with materials that are being secreted by a cell that are really large materials like venom or like a huge neurotransmitter. And we're not really caring what the concentration gradient is because these things are just packaged in vesicles and delivered to the plasma membrane. And then so when that vesicle fuses with the membrane, it ejects whatever's inside of it. Doesn't matter what it is, whatever's inside of that vesicle, when it fuses with the plasma membrane, is now ejected. Right? And it doesn't matter if it's more highly concentrated outside of the cell than it is inside. It's just, it now got released outside of the cell. And here's an illustration of this. So here's a vesicle. Again, not just kind of floating freely in the cytosol, but instead moving along what? Cytoskeletal element, right? And specifically a microtubule. So there's some motor protein walking along the microtubule, physically attached to this vesicle, walking it to the plasma membrane. And then once it gets to the plasma membrane, these things just spontaneously fuse together. They're both made up of phospholipids and cholesterols and integral proteins, and so they mix well together. Once it gets out here, they fuse together, and then everything inside here gets dumped into the environment outside of the cell. Yeah.
Would the cell grow each time it ejects something?
The plasma membrane does, yes, but then at the same time that it's doing this, it's also bringing vesicles in from the plasma membrane. Yeah, but yes, otherwise the plasma membrane would just continue to grow indefinitely. But at the same time, the cell's also doing endocytosis.
So if it's not an even amount, like it's getting rid of more than it's coming in, shouldn't it be?
Then the cell would be growing. Yep. But that doesn't happen. Cells don't typically grow that way. But as a cell is actively growing, it does have to put more and more material into the plasma membrane. Yeah. All right. So what is endocytosis? Basically the exact opposite of exocytosis. Except for now, it's a little bit more highly controlled. Because exocytosis, you're not worried about bringing something in that the cell might not want. With endocytosis, you are. And so it has to be more highly controlled. So cells trap proteins and other substances. And these are substances that are too big to move even through channels, typically. Like the material's just way too big even to move through a channel. You you can't pump it because it's too big for a pump. It's even too big for a channel. And so you've got to just wrap membrane around it and bring that in. So you have two main types. You have what's called bulk phase endocytosis. Bulk phase endocytosis, also referred to as pinocytosis or pinocytosis, however you want to say this. And so in bulk phase endocytosis or pinocytosis, the cell just takes in extracellular fluid and anything that's in it. Okay? Sometimes this is referred to as cell drinking because it's just taking in little pockets of extracellular fluid. And if there's something in there, it's coming in with it. Whatever's in there is coming in with it. Then you have what are called receptor-mediated endocytosis. Phagocytosis tends to be a type of this. So if you went phagocytosis and pinocytosis or pinocytosis, that's fine. But receptor-mediated endocytosis takes in specific molecules as it binds them. There's a receptor on the cell surface that triggers wrapping that material with plasma membrane and forming this vesicle. And then this vesicle is labeled in a specific way, and it's labeled with a material called clathrin, and that targets it to move into the cell versus being a vesicle that's going to move out. So now this vesicle is tagged, is targeted, and will oftentimes fuse with a lysosome, which will then break down whatever that is, whatever the cell binded. And then from there, the products of this metabolism can leave the vesicle via transporters as that vesicle is shuttled to different places in the cell. The proteins in the membrane of that vesicle get recycled, and many of those get shipped back out to the plasma membrane because many of those are receptors that are binding something the cell wants to metabolize. And so those proteins either get reused and just sent right back out to the plasma membrane, or they get recycled and turned into different proteins. And again, phagocytosis is a type of receptor-mediated, and some cells, even in our body, feed almost entirely by phagocytosis, by a type of receptor-mediated endocytosis. This is how they feed. Our white blood cells are this way. They feed, well, not all of them. Some of the white blood cells that we call phagocytes feed entirely by phagocytosis. They just metabolize whatever it is that they eat, usually some kind of a pathogen, chew it up, process it, and if that phagocyte can't keep going because it's a danger to the cell, then it just gets sequestered and clogged up somewhere. This is where you can get like a pus-filled, structure. It's just full of spent white blood cells that have swallowed up the bacteria or whatever it was there. Now it's a danger to your body because there might be toxins inside of it. And so here's bulk phase endocytosis or pinocytosis, cell drinking. It's just taking in extracellular fluid, and whatever's in there dissolved in that water is coming along with it. Coming along with it. And here's receptor-mediated. Phagocytosis is a type of this. So you've got these receptors binding specific materials, triggering the cell to wrap that area in membrane and form a vesicle. That then gets pinched off and it's labeled with that clathrin and then goes and fuses with the lysosome, metabolizes whatever's in there. Moving on. So here's phagocytosis. Here's a phagocyte. Could be an amoeboid cell or could be one of our white blood cells feeding on something by phagocytosis. You can find videos if you want to. They're a lot of fun to watch, watching our white blood cells chasing bacteria through the bloodstream. Pretty fantastic. Just watching them shoot out pseudopodia after pseudopodia. Pseudopod after pseudopod. Sorry, let's get my subject-verb agreement correct. All right. Any questions about any of this from Chapter 5? I hope you've enjoyed Chapter 5. I told you we'd finish it up today, and we have, with 3 minutes to spare. So if you feel like I owe you those 3 minutes, go ahead and hang out, and we can talk about some more stuff. Otherwise, Have a wonderful weekend.
Can you go back up a couple slides?
Yes, let me.
I know I can look it up myself.